Good morning, class. We are looking at chapter 5, integrals, 5.1, areas and distances. Okay. So what we are going to cover here in this chapter, areas and distances, the definite integral, the fundamental theorem of calculus, indefinite integrals, and the net change theorem. Finally, the substitution rule. That means we should be extremely comfortable with basics of integration. And so the formulas that we have seen many times by now, hopefully we are comfortable with it. Okay. So let me give you the synopsis of the section. So this is called a Riemann sum. Suppose a continuous function is defined on the interval of a to b. It's a closed interval. And if the interval is divided into n subintervals, delta x can be calculated as b minus a over n. X sub 0 is a, x sub 1 is a plus delta x, so on and so forth. Then Riemann sum is as follows. The summation of I equals 1 to n f of x sub I delta x, which is f of x sub 1 times delta x all the way to f of x sub n times delta x. X sub I is any point in the interval. This is the synopsis of what we cover. So by the time we finish the section, everything becomes clear. The idea is that we partition the interval of a to b into a few, maybe 4 subintervals just to begin with. If we go with 4, then we make up 4 rectangles. The width is b minus a over n is 4, so it's b minus a over 4. By the way, that delta x, which is the width, doesn't have to be fixed, but when we fix it and they all have the same width, it makes it easier to follow. Then the height for each piece is f of x sub 1, f of x sub 2, all the way to f of x sub 4. If we go with 8 rectangles or more, the same thing happens. This time is delta x is b minus a over 8 or more. And as the number of rectangles increase, the approximation gets better. This is the synopsis of what really the Riemann sum is all about. We can use the left endpoints, the right endpoints, or the midpoint rules. Now, you don't have to memorize the formula. I'll show you an easy way to sort of use this. For L sub n is delta x times f of x sub 0 goes all the way to f of x sub n minus 1. Okay, so this one class is f of x sub n minus 1. Okay. And for R sub n is f of x sub 1 to f of x sub n. Delta x for all of them is the same. It is the height that would be different. And for the midpoint, somewhere in between, that means the 2 endpoints, you add them up, divide by 2. And again, what does it really mean? It becomes clear as we go through that. The area is roughly equal to that summation. This is an approximation class. When will it become the actual area? When we take a limit and we let n go to infinity, it becomes the actual area. So what do we mean by that? Let's make some sense out of this by going over the concept known as a method of exhaustion. In the old days, when they didn't know how to find the area of a circle, they would inscribe it with a polygon, starting with a 3-sided one, a triangular shape, and then they would add. As we add to the number of sides, everybody can see a picture is worth 1,000 words. Everybody can see that as we add, the area of that polygon gets closer and closer to the area of a circle. That's the method of exhaustion. Okay. And as n goes to infinity, it becomes identical to the area of a circle. This is when they didn't have the formula a equals pi r squared. And we use the same thing for the area under the curve. If we have a geometric shape, we can use a geometric formula. If we don't, then how do we calculate the area under the curve? We use this method of exhaustion. So let me just quickly show you as an example. if I cut this into 4 sub intervals. So delta x is b minus a over n, and in this example would be over 4. This is delta x, everybody. All right, so there are 4 rectangular strips. Now, what is the height? Well, if I use the left endpoints, take a look. I use those points. And if I do that, look at the shape. Left endpoints. This is what we were discussing in the previous page. If I use the right endpoints as the height, so just for the sake of argument, the first one would be this one. This height would be f of a, which they called it f of x of 0. Okay. Now, if we go with a different color, such as, let's say, green one. So if I use the right endpoints, I use those points. And so here's the graph. And I hope you see we get different rectangles. We calculate those areas, and delta x is the same, the width is the same for all of them, but the very first rectangle, this is the height, which is f of x sub 1, or a plus delta x, so on and so forth. I can take any point in between, it makes no difference. It is not the area, it's a rough scale, rough estimate of the area under the curve. So I can get the midpoint. If I get the midpoint, just as an example class, so the midpoint would be here. The midpoint would be here. Okay. None of them is the actual area under the curve. All of them are approximations. And what happens? Approximation gets better as n gets larger. So here's a simple example to make some sense out of this. If we are looking at f of x equals x squared plus 1, the graph looks like, and we want the area between the curve and the x-axis. It looks like this. First, let me just show you the graph is supposed to be y or f of x equals x squared and shifted up by 1 unit. So the graph looks like this, everybody. Okay, we just want the portion between 0 and 2. So we have isolated it so it can show you precisely what's going to happen. I hope everybody's clear as to what's happening. So let me erase that part. So this is a parabola, and everybody knows that. So with that being the case, let's just look at delta x. Before we do that, how many pieces are we going to add? Let's start with some nice and easy numbers, such as 4. So if we go with number 4, everybody, then delta x becomes b minus a over 4, or 2 minus 0 over 4, or 1/2. Okay. And so what we notice is the bottom is going from 0 to 2. Take a look. I would highly recommend you draw a line segment. Okay. This is 0 to 2. So this is 0.5, 1, and 1.5. And I tell you why. Because even without a graph, that line segment is truly helpful. So I want to use the right endpoints, the left endpoints, whatever. So let's cut this into 4 equal pieces. Again, for illustration. Now, which one are you going to use? If I'm going to use the right endpoints, I'm going to use those points, everybody. Those are for the right endpoints. So what does it mean? I want you to go back to the line segment. That means for the width, I have delta x, which is 0.5. But for the height, for the first one, I have f of 0.5. So take a look at what happens if we do the drawing in this manner. And R sub 4 is this. I want to make sure that everybody's clear as to how we arrive at it. So we are looking at the right endpoint. So this is the first height, this is the second height, third, and the fourth one. So I want to go back to this line segment up here, everybody. What are we using? We are using all the endpoints except the first one for the R4. So 0 is out. We use 0.5, 1, all of them except 0, because we are using the right endpoints. So what do we mean by that? If we need f of 0.5 or 1/2, f of 1, so on and so forth. So this one is the width times the height, and so on and so forth. I hope everybody is clear as to why f of 1/2, f of 1, and what is f of 1/2 as an example? Well, put it here, 1/2 squared, 1/4 plus 1, 5/4. What is f of 1? 1 squared plus 1, which is 2. You can calculate the rest of it, and you end up with the answer. So I'm hoping nobody has any problem with simple calculation like this. Okay, it is tedious, it takes some time, but I hope you realize the usage of this line segment at the top that I have for you is going to be extremely helpful. So you won't use 0. Now for the left endpoints, everybody, if I want the left endpoints, here's the graph. Okay, here's the graph, which means, let me use a different color on the graph, which means I'm using this point, this point, this point, this point, and not the last one. Which means if I go to the top line segment again, left endpoints, all of them are good except the last one. I'm not going to use the last one. Okay, so L sub 4 looking like this. Okay, everybody. And same as R sub 4, you calculate, you come up with the answer. What I want to mention is that actually this calculation is not that difficult if you have done a portion of it properly. So take a look at what happens here, everybody. This portion is being repeated here. Meaning, when you calculate R sub 4, be careful with your calculation. Hold on to every piece. So for L sub 4, all you have to do, add half of f of 0, and you're done. So those two pieces are identical. That will help you with the calculation, everybody. Pay attention to the calculation. So the area is somewhere between the two. We don't know what the area is, but for sure somewhere in between the two. Okay, let's do the same thing quickly with larger n. So we're going to go with 8. Delta x is b minus a over n, and that becomes 1/4. And as far as your line segment is, again, you draw this. Okay, this is 0. This is 2. And you cut this carefully into 8 pieces, starting from 0, ending with 2. And so we want the right endpoints looking like that. So R sub 8, okay. What are you using for the width? The width is fixed at 1/4. What about the height? You use all of these endpoints except the first one for the right. And for the left, you use all of this, again, going back to this line segment, it's truly helpful. All of those except two. So take a look. So you have f of 0, f of 1/4, and so on and so forth. Again, you have an answer, and notice what's in common. So this portion is in common. So I hope you see If you calculate the first one, the second one really shouldn't be that difficult, and the area is between the two. Remember, previously was between 3.75, previous page, it was between 3.75 and 5.75, and now it's much better. And what does it mean? As we add to n, the approximation gets better. And that's really the idea behind this section. When we add to the number of rectangular strips, it becomes better. In fact, for this one, maybe even number 20 will do the job. However, if you let n go to infinity, it becomes identical. So what we just illustrated, it's in this page with formulas. I wouldn't worry about the formulas, but I'm going to quickly explain it. The same thing we just did in the previous page. Look at the left endpoints class. We start with f of x of 0, okay? That means the very first one is used all the way, not the last one. That's really the meaning of this part. Whereas for r, okay, you are using not the first one, but everything else here. See, delta x times those. And the midpoint says just go with the middle of the two. In other words, if you were to graph this, just to quickly show you. So if you have a line segment, let's just cut it into 4, just for the sake of argument, only because of the illustration, okay? So this is really your x of 0, this is your x of n, okay? And so what happens with the left endpoints, you use all of this, and f of those becomes the height, not x of n. For the right endpoints, don't use x of 0, use all of them. And what about the midpoint? The midpoint, sadly, you have to do it from the scratch and calculate it. So here's the midpoint, this point, this point. I hope you see how you can get to the midpoint. It's that. And if you look at the definition at the bottom, class, really refers to any point. When you have x sub 1 star, that means any point. So take a look at this graph. You cut it into so many pieces, okay? Left or right endpoints or anywhere in between makes no difference. Why? Because none of them gives you the area. All of them give you an approximation, and the approximation gets better as you add to n, and eventually as n goes to infinity. Take a look. So the limit as n goes to infinity becomes the area class, okay? All right, let's calculate this. And I want to show you how fast you can calculate this without really paying that much attention to the formulas. First, understand the function class is 1 over x. So f of x or y is 1 over x. And the limits are from 1 to 2. That means a to b is 1 to 2. Delta x is b minus a over n. So understand, you can graph this, and we want the area between 1 and 2. Again, if we were to sort of graph, what we are looking for would be, okay, if this is 1 and 2, assuming this is 1 and this is 2, this is the area we want. Okay, class, that's the idea. And so here's 1 and here's 2. Here's my line segment. So first and foremost, n equals 5. Delta x is b minus a. That means 2 minus 1 over 5 or 0.2. And f of x is 1 over x. So we need to cut this into 5 pieces. Okay, and we said it's a 0.2. So this is class 1.2, 1.4, 1.6, 1.8. So now let's find L5 because n is 5. I don't even really pay attention to that because my line segment is really helpful for me. So it will be delta x, which I have it as 0.2, times f of I use all of these points except the last one. So I want f of 1, f of 1.2, f, and what is f, by the way? 1 over x. So 1 over 1, 1 over 1.2, so on and so forth. Take a look at the line segment. Again, I did the drawing for you here, and see what happens here. This is f of 1, f of 1.2. And you do it with a lot of decimals. Now for the right endpoints, everybody. This is a better one. For the right endpoints, I just don't use number 1. I use all of them except number 1. So again, notice what we can use, everybody. This portion is being repeated. So that really helps with the calculation. I hope you see that, and we end up with this answer. Now, what about the midpoints? Now, the midpoints, sadly, we don't have any choice but to actually calculate all of them. So what would be the midpoint? Let me use a different color here. So over here, this one is 1.1. I hope everybody can see that. And then you just add delta x, which is 0.2, and you get 1.3. Okay, okay, and 1.5, 1.7, 1.9. Just keep up with delta x. And of course, you have to calculate each one. We call it m sub 5. And by the way, that's a better approximation than the other two. So I wanted to show you with details because sort of, midpoint is sort of new. We did the left and right endpoints in previous pages. But for the midpoint, so we are using 1.1, 1.3, f of those. Where delta x, of course, is fixed at 0.2 or 1/5. And we end up with, as I said, a better approximation compared to the other one. In fact, you notice it's in between, because what happens is that one will overestimate, this will overestimate class. The actual area, and this will underestimate. And how do you know that? Again, underestimate. It has got to do with the graph, okay? So to give you an idea, because the previous page I think showed it better, so let me just quickly go to the previous page and show you this under and overestimate quickly. It's easier to follow it from the previous page. So I hope you see the overestimation here. I'm going to just write over, and this is under. Okay, so clearly for the right endpoints, we get an area which is larger than the actual area. For the left endpoints, we get an area which is less. That's why the area is in between. So overestimate means it will be larger than the actual area, and under means less. And how do you know that? Really, the graph tells you. For example, because this is increasing the right endpoints the way it has it, and it's concave up, increasing and concave up, will overestimate with the right endpoints, underestimate with left endpoints. Again, concavity, increasing, decreasing. So if you want to put that, so it's increasing. Let me use a different color here. It is increasing, and it is also concave up. Okay, that's why. Because if it's not going to work out that way. You really have to look at the graph. All right. So we are looking at this concept of the left and right and the midpoint. And the fastest way to calculate is what? Use a line segment. Distance, if you recall, D was RT. Everybody remembers that. And that is the same problem, the distance problem, okay, is the same as the area problem, okay. If the when we look at the distance, remember the velocity times time, it gives you the average velocity times time. If you do 50 miles per hour, on the average over the course of 3 hours, you cover 150 miles. Okay, but what if the velocity varies? Then it becomes the same problem as a distance problem, okay, which requires geometry. The geometry fails, and therefore you go to calculus. So having said that, here's an example. You already know the answer is 100, but just we want to discuss that with the concept of area under the curve. So we'll see the similarities between a velocity problem and a distance problem. Okay, so D equals RT 50 times to 100 miles. So if we treat the vehicle's velocity as a function V of X, V for velocity, and that's fixed at 50, so that means Y or V of X is 50, which is a horizontal line, okay? Over the course of 2 hours, so along the X-axis, okay, we have 1 and 2, it's fixed at 2, it's the vertical line, if you will, okay? And the velocity is fixed. We can calculate the area, okay, as the width times the height, and easily we can come up with the answer, which is 100 miles. So I hope you see you can treat this as an area under the curve of the velocity function. So the distance can be, if you happen to have a function which is positive, the area under the curve. Now let's do the same thing with something slightly different. The velocity of a moving object is given by a function V of X equals 3x. I hope you realize Y equals 3x in essence is a line with the slope 3 that goes through the origin. I hope everybody remembers the basic graph, okay? I'm going to use geometry, okay, to find the area under the curve during the first 3 hours between 3 and 5. So let's look at the graph. The graph is Y equals 3x or V of X equals 3x. So Y or V of X equals 3x. And so how do you find the area? Area is 1/2 base times the height. I hope you see that this one has the following coordinates. The x is 3, and the y or v of x is 3 times that, or 9. Okay. Okay, class. And so 1/2 base times the height. When we have a right triangle, the base and the height are the 2 legs. So 1/2, 3 times 9, and we get 27 halves, and that would be miles, okay? Now between the 3rd and 5th, let's do the drawing between 3rd and the 5th, and here's how it looks like. How do you calculate that area? You have 2 choices. You can just calculate the area of a trapezoid. I hope you see the trapezoid. This is one, let me just, this is one base class, smaller base, larger base, and this is the height, okay? Or calculate the area of this rectangle plus the area of this triangle. However you do that, it's just a geometry, you can figure it out. I don't think it's going to be any problem. Remember that this was 3, okay? So therefore this point has coordinates 3 and 9. Therefore you have this height of 9 here. And this from 3 to 5 is 2. You can calculate that. Now this portion, okay, when you plug in 5 into 3x, you get 15. So let me just quickly write those pairs so you see how that works. So this one, we had it as at 3 and 9, right? How about this one? This one has x coordinate 5, and then 3 times 5 is 15. That's why this distance is 15 minus 9. Okay. However you want to look at it, you can calculate the area of a rectangle, the area of a triangle, and add them up. Or just the area of a trapezoid. And I hope you remember the area of a trapezoid. Let me just write it here, is 1/2 the height, b plus b lowercase and uppercase, or b1 plus b2. It's just a matter of, how you look at it, class, okay? It's just a matter of how you look at that. So, in short, the area under the curve and the distance problems seem to be the same. All right, finally, a couple of simple questions. What if we want to use the definition to find an expression for the area under the graph, okay? Remember, the area uses this definition. This is the area. This is the class. So we are going to come up with that, given the f of x. So first and foremost, we're going to come up with delta x. Delta x is b minus a over n. So remember, a is 4 and b is 7, everybody. So let me just write that also. So this is going to go from number 4 to number 7. This is A, and this is B. Okay, class? All right. So we can calculate delta x, b minus a, 7 minus 4 over n. And then as far as a is, x sub I is concerned, is a plus I delta x, class, okay? X sub I is a plus I times delta x. That is the ith one, if you remember, and you go back to those definitions, starting with a plus I delta x. Okay, so with that being the case, let's do that. So this is 3 over n, and x sub I is a plus I delta x. A starts with number 4. So 4 plus I times delta x, which is 3 over n, and we get 4 plus 3 I over n. So again, quick recap, look at what we have at the bottom. First find delta x, then find x sub I using a plus I delta x, and maybe I graph this for you one more time. Remember, you have a line segment that goes from A to B, and you cut it into pieces, however many pieces. This distance is delta x, everybody, okay? So starting with A and then I times delta x, okay? The first one, the second one, so on and so forth. All right, so let's replace this, therefore, okay? The limit, okay, and by the way, this is R sub n. I want you to know that when we write it in this format, is really the R, the right, this is referring to right endpoints, okay? So to the right endpoint. So we are going to replace, so we have f of x sub I delta x. So what is f of x sub I? This becomes x sub I, this becomes x sub I, okay? So maybe I write it underneath so everybody can see what I mean by that. Again, so f of x sub I is x sub I cubed. Let's write it. X sub I squared, my apologies, plus the square root of 1 plus 2 x sub I. So that's the function, right? Now f of x sub I. So what is x sub I? Four plus 3I over n. Let's replace it. Let's replace it. See what you get. So 4 plus 3i over n. So we are replacing x of I with 4 plus 3i over n. And we can leave it like that for now. This is just the expression we wanted to come up with. In other words, given f of x, how do you write the Riemann sum? This is the Riemann sum, everybody. Okay, this is the Riemann sum. I hope everybody is okay with this. So in essence, you are writing the Riemann sum. Okay. All right. Let's quickly switch gears. What if the Riemann sum is given? How do you find the functions? And sometimes it's not unique, but some of them are very obvious. Before even you start working on it, you may be able to see that in essence, this is your delta x, right? Okay. And so the function, so it could be, and the reason you know this is delta x, it doesn't have an I. If it doesn't involve I, it's just a constant or delta x, okay? So this is, again, go back to this one and compare it, okay? We're gonna compare that in a moment. And this seems to be like a square root function, square root of 1 plus something. Are you with me? So just you have an idea that the function should be something like square root and 1 plus something. 1 plus a square root. 1 plus some function. All right, so what is it? First, we have this, and we know delta x in a matter of comparison. Okay, we are comparing these two. Delta x seems to be this one, and this should be f of x of I. Okay, so this first piece is your delta x, okay, which is b minus a over n class. This is b minus a over n, and this is square root of 1 plus 3i over n, your f of x of I, okay? So, well, one easy way, this is 3 over n, b minus a over n. So 3 is b minus a, could be any number. For example, you can say 3 and 0, okay? You could say 1 and 4, I mean, you can do that. But let's stick with 3 and 0, the easiest one, just as an example, and practically you're done. This becomes 1 plus x. So let's look at it. So delta x is b minus a over n, x of I is a plus delta x, and b minus a over n is also 3 over n, okay? And a plus I delta x is 3i over n. So let's just make sure we understand that we have, in essence, two equations, two unknown, okay? And this is x of I, 1 plus, this seems to be x of I. And so if you choose a to be 0, class, if you choose a to be 0, b becomes 3. If you choose a to be 1, b becomes 4, just as an example. And look at one simple example. If you go with delta x being 3 over n, x of I 0 plus I delta x, I times 3 over n, and that's exactly what you have here. Again, partly it's by inspection, and it gives rise to the following: y or f of x. Y or f of x is square root, just right here. As I mentioned in the beginning, you have an idea, really, you have square root of 1 plus x. Do you follow what I'm saying? So even if you notice it in the beginning, aim for that, it should be 1 plus delta x. All you have to do, figure out delta x is that, so what is my a and b? Okay, and you're done. But I want you to think about how about this, and then work it out. If you choose, instead of square root of 1 plus x, if you choose just square root of x, and instead of 0 to 3, if you choose 1 to 4, look at this and see as the method of the previous example, the method of the previous example. See now if you can go back to this. I hope you see that will work also.